Welcome again to Grasshopper for Rhino, ABCs, 1, 2, 3s. As you can see here, we've moved through the params, the maths. We're getting into the sets, which are all these nodes over here in purple. I've now broken them down into pretty simple algorithms, and I'm starting to pull out some half-decent ones. We've gone through lists under sets. We've gone through sequence under sets. We ran into a problem on lists under sets. In a sense that what list item is, that's mainly what I thought. Well, I ran into the problem of thinking it was what set member does. We're going to see that in this list as we get into sets of sets. And I think I resolved that down near the bottom of this one. Actually, I don't. I resolved that in a sense of starting to understand what item index does through a sort list and creating a list. It's a different type of thing. I'll try and talk a little slower, even though that seems to be impossible for me. So let's jump right into it and see what we got going on. So what we have is we're pulling out a node on character sequence, which has a count of 10, a character pool of the alphabet in caps, and a format if you actually want to change that those numbers. And we may get into that a little farther down. I'm going to create a set out of that. Basically, that's all it does. It takes that sequence and pops it into a set and gives it list items. And there's your list items mapped. The next is the character sequence. I did want to talk a little bit about the fact that these wires are kind of in the way half the time. On any input, you can go to wire display and put down faint and hidden. If you're trying to swap faint to hidden, you're going to have to get a plugin. I think it's called MetaHopper or something. I don't know. It's called something like that. Anyhow, set difference is I've taken two sets. I've taken this one that had the set of 10. This one has a set of 5, and the distance is the 5 that aren't within this set. So this set minus that set gives you this set. Set difference. Set difference S, which actually I'll have to look it up what that means. The only difference is this one is a collection of objects present in A, but not in B. This is actually sets that are present in A or B, but not in both. So it does come out different. So you can end up having the same set as you go through the difference of the count. If set A has, if we look into it, a set from A to J, and this one has 8 count, it's basically going to show what's not in this count. And if I go over, it's going to go plug that one in over. So you get a set difference as well, which is a little different than this one, which describes itself, like I said, A but not in B. This one is A or B but not both. So try and wrap your head around that as data and then plug that in. Good luck into some geometries. I'll try and show evidence of that later. Probably won't use characters. I'll probably use data as in numbers. The whole goal of this, if I zoom out here and I'll remember to come back in here, is it gets more and more complex as you come to the end of sets and then go into vectors. But we're going to get into the tree data here. And at that point, I'm going to point us back after I do some basic grafting and flattening. I'm going to have to point us back to Mode Labs and its intermediate and advanced tutorials on data trees. Otherwise, I just keep running into more and more problems. This one where I'm dealing with format and cultures, that's pretty tough for me to understand the languages and different culture languages, but I try and resolve problems as I go. All right, we're watching the time, 3 minutes in. Here we have the character sequence that is a set intersection. You might want to relate the intersections and unions and differences to Booleans in Rhino, and you might want to relate those to, what are they called in the intersections here in Grasshopper? They are called solid differences, intersections, and unions as opposed to Booleans. Anyway, so there is your set intersection. You've got your initial one, which has the 10 characters in it. This one that has the first 4 within it, and it is finding the set intersection between the two, and that's exactly what it gives out to you. This one, if I take the 4 and I keep the original 10 and I take this one, it chooses the ones with the majority. So if it's got 8, 10, and 4, it's going to choose the 8. If it has 1, 4, and 10, it's going to choose the 4. And it goes towards the majority that holds the most. And definitely what's contained within, whatever's contained the most in every set. And the top 2. So here we go, character sequence into set union. You can grab that union. I'm going to lower it to here, and you're going to see you have 0 through 9 coming out of this set, but it only adds to that union if this set climbs higher than that to add to it. So even though I go to J, it's got to get to K and up for that to actually have an effect on that set union. All right, into another set, you've got Cartesian product. So you have your set, you're running through the digits. This time I've gone back to a series and out of a character set, and I have a start value that I can grab 2 sets and multiply them both together, and that's exactly what I end up with. Set 1 and set 2, and they come in as a double list. So if I set this one back to Here, it's going to be the same list twice, but you can start to play out the start factors in those, and you can multiply the products of those Cartesian, which is basically create a Cartesian project for two sets. Sorry. Let's read it exactly, of identical cardinality. So you have to keep the count the same on this, otherwise you're going to run into problems. So if I bring this count down to 9, it's going to default. The other one here is disjoint, and I believe that is whether something is disjoint. Now, what makes a set disjoint again? Set A and set B. It is false currently. What would set that correct equal is if all of a sudden they actually have what is similar between those sets. So if I have a start of 11, are they disjoint means they have nothing in common. So as soon as I get to starting at 11, this one ends at 10, it's going to say, okay, we're cool to be disjoint for a while. But anytime we bring a set that overlaps, it's going to say, we're not disjoint anymore. So it's cool to be disjoint with people, I guess. All right, here's the members index, which does what you might have thought the list index did. You've got data coming in. So I've got a 2 coming in. I've got a 5 coming in. And I'm seeing in that setup here if those 2 are within that set. And they definitely are, and it says the index of where they come out. So I'm trying my first edit here, which is kind of cool. And I'm taking a look at this series, which runs 0 through 9. All right, I tried a second edit. I just cut that one out. I didn't have it set right, and I'll show you why. For replacing members, this is less parametric, but you can see I have a series of 10. I want to replace the numbers starting at 0, or I can start the numbers with whatever, with 4 numbers. And you set the count to how many you want to replace, and then where in that set you want to put it. So if I start at 0, but you do have to match your data. It has to be the same number in find and same in replace. You're going to want to use list length to probably solve a lot of those problems. So forget the first one. I just ended up cutting it out. I didn't have it set right. I apologize. Subsets are, is this a subset of that? Well, if this start runs at 5 and I only go to a 5 count, that will still be a subset of here. But if I take this count up higher, it's going to end up turning false because that subset is not within that initial set, which is from 0 till 9. So even if I brought this one back to 0 and I take this subset, it's going to remain true all the way through to 10 digits. But if I bump that up to 1 or 2, you see as I get that up to about 8, 9, and 10, then that's going to say, no, you're not a subset. So something interesting to see if one thing folds into another one. Cartesian product I used earlier, but I'm using that same data again to come up with a Cartesian product, which is grafted two things coming out of the same series. I could change this number slider to get different points at different points here. But what happens is delete consecutive is really nice. It takes all that data that's actually the same, which is what's happening here, and reduces it back down to a grafted list of single digits. So instead of 2 3s, 2 2s, 2 1s, 2 0s, sorry to read out of order, it's brought it back down to 1. So that should make a little sense, Cartesian product being used to resolve that if the digits are the same, if the data is the same. Find similar members is the same. What is similar between this count and this count? Well, if the count is 4, obviously, if my data coming in is 0 through 3 and my set here is 0 through 3, it's going to hit members S closest to D. It's going to hit those 0 through 3, and then the index is going to list on there as well. So finding similar members is pretty simple concept as well. Let's keep rolling down. This is the final one. No, it's not the final one. I've got 2 more to go. This is where I wanted to get into figuring out what to do with sort, list, and key values. I really like this tool. And to wrap my head around here, we've got 8 minutes in, so I can do it. If I say search for 2, it'll go to keys, or say search for 4. It'll go to 4, find 4 within keys, and index that at 3, then send the index down to 3, and tell me exactly what's coming out as the value 9. So that's a pretty darn good tool. So if I say find 2, index 1 in values tells me 7, and it changes here. So keep doing that until you figure that out. Very exciting tool. 8, locate it at index 7. Go to index 7 in values and tell me the value is 13. Very cool. My kids are in the house making tons of noise, and in figuring that out, that allowed me to go back to here, which we're going to show a little highlight of what list items does. If I pull a set in and a set in, and I share all that, I share that data within a merge. So I have a series that starts here. It goes, and this one starts at 14. Sorry, it goes up to 14. This one goes up to 10. I've basically got a character set, which you can take a look at what that is. That's 0 through 13. It's nice that it shows that digit on the end. Bring that into the keys and the values. My boys are really ending well, but I'm not going to start this video again. And you can see basically I have the full set of 0 through 13, and I want to know the item index of that first series, item being whatever numbers I want them to be. It'll index those numbers straight over here to that list and that item coming out, which is these items, 0 through 13, it's going to tell me where those ones actually ride back into the keys. Now that's a little hard to think about. You're going to have to kind of play with the numbers to play off of that. I always find going back to the basics. Why doesn't it work at 0? Why would it work at 1? How do I end up indexing these 3 things? So this index does start to make a little bit of sense down through the end of here as a list index coming out of these two. An item index of where we're indexing that, but then the list index is actually making a little sense of that. I'll try and explain that again as I get into the next video. We'll roll over it again. Thanks for watching, but do keep in mind that that item index does not behave like a members index that we used earlier. Thanks for watching. We're going to dig deeper, go harder, and see what happens when we enter into the text lines, which are pretty wicked as well, and then tree data when we get into these final ones, relative items, path mappers. You're going to realize how complex it gets. And to get your head around how tree paths make geometries beyond lists, you're going to have some incredible scenes, geometries, worlds, whatever you want to end up doing and rendering out. Pretty cool tool set. Anyway, thanks for listening. We're over 11 minutes.